you so much for the introduction. As was said, my name is Labell, and today I'm going to be presenting our research focusing on reverse engineering checksum algorithms from binary data messages. So in terms of what I'm going to do today, I'll start by talking about why this problem is important and why a tool like ours could be useful for a user. Then I'll talk a little bit about what we did, how we solved this problem, and then finally I'll talk about how we evaluated our approach. So reverse engineering binary message formats is an important part of security research. Our work focuses specifically on reverse engineering checksum fields from messages, and one motivation for inferring checksums is that they're often used in systems to protect against corrupt or untrusted input, and will end up acting as a sort of gatekeeper to a system. So imagine that you're an analyst trying to discover security vulnerabilities in a system. You might have a set of unknown messages that you've seen being sent to the system and that the system accepts. But before you can explore the system for vulnerabilities, you'll need to construct your own messages that will be accepted by the system. So let's say you construct a couple of messages and you attempt to send them to the system. So the problem you might run into is that messages without a valid checksum won't be accepted by the system, essentially producing a bottleneck in your workflow until you can discover the checksum algorithm used. So the point I want to make here is that reversing a checksum calculation might not be the main goal of the analyst, but for this reason, it is an important obstacle that has to be overcome on the path to some larger goal. And so this is not a super trivial problem, especially when input messages are long. Finding relationships between bytes is time consuming and tedious for a human to do. And so this is why we thought that an automated approach to this process could be really helpful. So here's just a short overview of what we did. We started by collecting problem instances from reverse engineering question and answer sites and existing internet protocols to compile a corpus of these types of problems. We then developed a program synthesis approach, which takes binary messages as input and automatically produces runnable checksum algorithm code as output. And then finally, we evaluated our approach on the problems in our corpus, showing that we correctly inferred the checksum in 12 out of the 14 cases. So again, the first thing we did was to look for places where we could find examples of this problem. So we got on reverse engineering question and answer sites, which were a really great source of information because they allowed us to see problems that real people in the world were facing, as well as how experts approach them. And so we wanted to kind of get a sense of the nature of the problem, which we could then formalize. So we collected problem instances in which users provided a set of binary messages. The example shown here is actually for an air conditioning unit that had a protocol that someone wanted to reverse engineer. And so I'll be using these messages as a running example as we go along. So we ended up collecting a total of 37 problems for our corpus, and we classified them by the type of error detecting algorithm described by the post answer. And so we ended up with a handful of CRCs and checksums, a hash code problem, some questions that we didn't have answers for, and yeah, so the next thing I'll do is talk a little bit about how some of these algorithms differ and why we decided to focus specifically on checksums. So checksums and cyclic redundancy checks were the two most common algorithms that we encountered on the Q&A sites. And although they are both used to detect errors, they are fundamentally different algorithms. And so we just wanted to talk a little bit about their differences and why we decided to focus specifically on checksums. So as some background, a CRC uses polynomial arithmetic, and it treats the message as a long binary number and divides that message by another fixed binary number. The remainder of this division will then form the check value. But on the other hand, a checksum will repeatedly apply a binary operation across the bytes being checked, and checksums are generally less resource intensive to compute, so they're often used in systems that have resource constraints. So apart from just the algorithms themselves, we also noticed that there were some differences in the problems of reverse engineering these algorithms. So we noticed that the problem of checksum inference is not quite as well defined as CRC inference is. So there's a formal model for CRCs called the Ross-Williams-Roxoff model, which can be parameterized to behave like most CRC algorithms in use today. And there's also a tool called CRC Revenge, which can be used to reverse engineer a CRC calculation. But on the other hand, we noticed that there wasn't a formal model for describing checksums or really any tool for reversing them. And so we wanted to fill this gap. So to do that, we designed a grammar for a generic checksum algorithm based on the problems that we collected from the corpus. And then we implemented an approach to search for checksums given binary messages as input. So we spent a lot of time hanging out on these internet forums, and we noticed that users often had a couple of questions. First, they'll want to know, is there a checksum in their messages as opposed to some other type of error detecting code? If there is a checksum, then they'll want to know where it's located, and they'll also want to know how it's calculated. And so given these needs, when a human is tasked with reversing a checksum calculation, they want to determine three things. First, they'll want to determine the payload. So they want to find the portion of the message protected by the checksum, which is shown here in blue. They'll also want to identify the checksum itself, shown in red. And then finally, they'll want to discover the checksum algorithm, which takes the payload as input and returns the checksum as output. So based on these goals, we divided the problem of reverse engineering a checksum algorithm into two subproblems. So first, we perform a search over the message space for parameters describing the payload and checksum locations. And then given a candidate payload and checksum, we perform an enumerative search over our algorithm grammar in order to synthesize a checksum algorithm. And so the result of these two searches is a checksum parameterization, which our tool can either report directly to the user or it can actually output code implementing the result for the user. So I'm going to begin by talking a little bit about the message search step. And again, the goal of this step is to enumerate all possible payload and checksum locations. So given binary messages as input, we'll start by partitioning the messages into arrays of width size integers. So in this case, width is 8, so we're partitioning the messages into bytes. We then enumerate all possible payload and checksum locations, which we encode using the parameters payload start, payload end, and check index. And so one assumption that we make here is that all messages in a given problem instance use the same checksum algorithm. So therefore, our goal in this step is to make sure that the message bounds we identify work for all messages, even if they vary in length. And so this step will give us candidate payload checksum pairs for each message. And so once we have these locations, we can then perform a search over our grammar in order to find a corresponding checksum algorithm. So again, at this point, we have candidate payload checksum pairs. And now we're going to perform a search over our algorithm grammar in order to synthesize a checksum algorithm. And so the idea here is to perform a brute force search over all possible checksum algorithms in our grammar. For each candidate checksum algorithm, we evaluate that algorithm on the payload checksum pairs from the message search step. And so to verify a message, we check that for all of the messages, the synthesized algorithm produces the checksum as output, given the payload as input. And if it does, we can report that result to the user. So a little bit about our algorithm grammar. So we designed this grammar based on the instances that we collected from the forums, and our goal was to be expressive enough to say what a human said when they looked at these problems. So of course, if we had different examples, they might have caused us to do different things or design our grammar differently, but this grammar can express most of the problem instances that we collected. So each checksum algorithm in our grammar has a fold operation, which we call fold op, which is just a binary function like addition or exclusive or that we use to combine elements of the payload and accumulate a value. So checksum algorithm is just performing a fold higher order function over the payload. The operation is given by fold op, the x's designate the payload, and the initial value is 0. So in the example shown here, the fold operation is addition. So we're just summing up the elements of the payload. So a checksum algorithm can either be a fold operation alone, a fold operation with a unary final operation, or a fold operation with a binary final operation, the integer literal that we call the magic value. So after we perform our fold operation over the payload, we can optionally perform an additional finalizing operation on the result. So in this example here, once we've summed the elements in the payload, we perform a binary final operation on the result, which is just going to XOR the result with the magic value OX55. So once we've synthesized an algorithm, we can use some optimizations for validating that algorithm on the messages. So one thing we can do is identify the magic value in constant time rather than searching over all of the different possibilities. To do this, we use inverse functions of our binary final operations in order to identify the magic value of the first message. And then we just verify that this magic value holds for all of the other messages in the problem instance. We can also, also if all messages are not the same length, then there's some benefit to checking the shorter ones first. Because we rule out algorithms by finding contradictions, we don't necessarily need to check all messages in order to prove that a certain parameterization doesn't work. And so by using the shorter messages, we can find these contradictions quicker. And then finally, we use a dynamic programming approach for longer messages, which allows us to verify a synthesized algorithm for many different candidate payloads quickly. So the idea here is to save the fold result for each candidate payload location. Then when we're trying to compute a fold operation over a payload of size n, we can use the result that we save for a payload of size n-1 and perform the fold operation once instead of many times over the entire candidate payload. So when our algorithm does find a parameterization that works for a set of messages, we can either return that parameterization directly to the user, in which case they'll have to have some idea of our formal model for representing checksums. But we can also return runnable Python code actually implementing the checksum algorithm, as well as generate unit tests, which will allow the user to validate a message, or will allow a user to validate the synthesized algorithm on a set of messages. And so doing this allows a user with not much experience or much background with checksums make meaningful use of our tool. And so we evaluated our approach on our corpus, and we focused on problems that we had answers for and whose answers actually used checksum algorithms. Additionally, we collected an IPv4 header and an ICMP capture to test our approach on. So the first 12 are parameterizations which our approach successfully found, meaning that they matched the answer in the forum post or the answer given in the formal spec. And then there were 2 degenerate algorithms that our approach was unable to find. So for these 2 algorithms, our approach can express the location of the payload and the checksum for these 2, but the grammar isn't expressive enough to synthesize them. So the first problem computes an 8-bit checksum modulo 257. Normally we would see the modulo operation being used in order to just extract the least significant bits and make sure that the checksum fits in its 8-bit field. This algorithm computes a checksum modulo 257, which doesn't necessarily guarantee that it fits in a byte, which is a strange outlying case. And then the second algorithm performs 3 final operations instead of just 1. Because we could express almost every checksum algorithm that we collected in terms of a single final operation, we didn't add this class of algorithm to the grammar based on just this one example. But if we do find more examples that match this design pattern, then we'll want to add this sort of thing to the grammar. And so that's one nice thing about our approach. We can express an entirely new class of checksum algorithms just by making some small changes to the grammar. And so we're really excited to continue collecting more problems for our corpus and continue improving on the grammar. So we also found that our tool often found multiple results for a single problem instance. And so the reason for that is just that there are often multiple checksum parameterizations that are consistent with the data. Humans on the forum stop after they find one, which is useful because it lets us know that there exists a checksum in the data, but it doesn't necessarily guarantee that the solution that they pick is optimal. So we return to the user all parameterizations that work, but we employ some common sense heuristics in order to rank the results for the user. So first, we expect checksum fields to be more random than other fields in a packet, which means that they'll have higher Shannon entropy. So therefore, one thing we do is we sort the results by the Shannon entropy of the checksum index. And we also skip parameterizations in which the candidate checksum index is constant for all messages, because that's probably a good sign that it's not a checksum field. We also expect the payload to include as much of the original message as possible. So we also sort the results by the length of the payload. And so one avenue for future work is further developing and improving on these heuristics. One thing we'd like to do is prioritize simpler algorithms over more complex ones, in which case we'll want to apply the minimum description length principle to our results. So just to wrap up what we talked about, we started by collecting problem instances from reverse engineering Q&A sites and existing internet protocols to form a corpus of these problems. We then developed a program synthesis approach, which takes binary messages as input and automatically produces runnable checksum algorithm code as output. And then finally, we evaluated our approach on the corpus problems, showing that we correctly inferred the checksum in 12 out of the 14 cases. And with that, I'm happy to take questions.
Thank you very much, Lauren. So we have time for questions. If you have a question, please just raise your hand in Zoom, and then I will unmute you. So maybe I can start with one question. So first of all, maybe I missed that, but I was just wondering, for these algorithms, how long did it take to synthesize the correct algorithms for the corpus that you used?
Yeah, so all of the problems in our corpus were relatively short. I think the maximum length of messages were 64 bytes. And so that ran within seconds. So like longer messages definitely took a lot longer. I think we did some micro benchmarks and found that 300 byte algorithms took like 51 minutes. So definitely as you get longer messages, the runtime is going to go up by a lot. But our hope is that it'll save a human considerable time.
Of course. It seems also, because essentially I understood that you perform an enumerative search. So it seems key to the fact that you can actually find the correct algorithm in the end is that you somehow picked the right grammar. You kind of identify what are the common patterns in these checksum algorithms. But as you also pointed out when you evaluated this approach, you showed that in two cases your approach did not manage to synthesize the right checksum algorithm. And in one case, I remember it was because you said that our grammar only considers one final operation at the end of the fold, and this one required 3. So I imagine, okay, if I extend my grammar to include the possibility of more operations, then I could probably, probably would manage to synthesize correctly this one as well. But there is a trade-off. The more I extend the grammar, the more it's going to take to do an enumerative search. So where do you think how do you think is the right way to reconcile these conflicting So if you have a more expressive grammar, you can probably synthesize more algorithms, but then the time to synthesize also goes up. So
yeah, that's a good question. Yes, I think the first thing that we would want to do is first see what other algorithms are common. We didn't add this example for that reason, that we'd only found one example. And so, yeah, I think it's just figuring out what's out there and then kind of considering the performance trade-offs that would happen if we decided to include those. So yeah, I think it's a problem that I would have to think more about, but we certainly are looking for more algorithms to include in our grammar. So it's definitely an important consideration.
thanks.
Can I ask a question, Marco, or is there a hand up?
Sergio, the other speaker in this session, is asking a question. So he's asking, is it correct that the technique is unable to identify synthesized checksums that are hash functions? And if so, are these kinds of checksums easily identified by users, or do they not fit the problem in some other way?
Yeah, so if I understand the question correctly, it's about hash functions. And yeah, so that's one class of algorithms that we can't synthesize. So the idea here is we focus on checksums, but CRCs and hash functions are also used. And so our approach is nice because we kind of divided it up into two steps: a message search step, which searches for locations of payloads and checksums, and then the actual checksum synthesis. But I think conceivably you could like change the checksum synthesis part to synthesize CRC algorithms or hash functions. And so we can kind of reuse the message search part of our algorithm and just identify different algorithms like hash functions. And so that's something we've talked about doing in the future, creating a tool that kind of marries reverse engineering checksums, hashes, and CRCs, which wouldn't be inconceivable because hash functions have formal specs, and as long as you check all of the hash functions that are out there, you'll probably get an answer.
Great. I think we have time for one more question. I think Ali, maybe you wanted to ask something before?
Yeah, just a comment first. I think that hash functions, at least cryptographic hash functions, are very complicated. And so yes, you could say, is this, this variant of SHA or something like that, but trying to actually reverse engineer them from scratch, would be, I'm thinking, impossible because they're so carefully engineered. The question that I had was, is there a sense in which, so checksums they're not about making things sort of hard or obscuring. Is there a sense in which your grammar identifies all the optimal ones or something, that the bizarre ones that you couldn't handle, maybe they're just bad? Is there a sense in which you can cover the space of actually good ones?
Yeah, so I think, yeah, perhaps the really weird ones, if I'm understanding the question correctly, are ones that, yeah, our algorithm grammar couldn't synthesize. And so we tried to come up with ones that if a user puts in or gives us some input messages, and their checksum algorithm conforms to our grammar, then we'll be able to synthesize it. And we just hoped that our grammar would be expressive enough in most cases. So in most well-formed algorithms, we would be able to synthesize. But yeah, you're certainly right that a lot of weird checksum algorithms in which people do strange things would not be found.